So hi, I am Anubhav Prakash. I'm my fourth year. I'm doing BSMS in physics from IIT Madras, and I'd be giving a talk today. And just let me share my screen first. Yeah, I hope you guys can see. Can you confirm if you can see my screen? Can anyone confirm if they can see my screen?
Yes, yes, it is visible.
Yeah. So the talk is going to be on Polya's recurrence theorem. So just don't let the topic confuse you that it is the only thing that I'm going to discuss. It is basically the main idea behind the lecture, but the main thing that I want to express or convey to you in through this lecture is how is basically its amazing proof and the intuition and the insight we get into the subject from this way that I'm going to prove it. That gives me quite satisfaction when when I studied this topic. It gave me quite satisfaction that while reading the proof and the approach it took and how interconnecting across different mathematical branches this uh, this whole topic is. So I just want to give that satisfaction to you guys also. So that's the main reason I chose this topic. And I believe that this lecture quite needs a small overview of what I'm going to talk about, so it is clearer to you guys that why and when I'm doing what. Mm, Yeah. So it is going to be a general proof-driven talk on random walks, where I use a special approach that we use in graph theory called Markov chains. I'm going to explain what Markov chains are. And why did I choose this topic? It has quite a lot of everything of mathematics. It has graph theory, my favorite field, and it has a bit of probability, a bit of combinatorics, a tiny bit of knowledge of infinite series, and a large bit of pleasuring mathematics ideas that every math loving person loves to hear. So we start by talking about relation between graph theory's topic Markov chain and a special property of it, and then relate it to a random and special property of Markov chains, which makes things interesting. Wait, I mean to say that we relate it to random walks and a special property of Markov chain that makes the relationship between them interesting. And it is this special property which we'll talk about, and a bit of mathematical beauty that is hidden inside different dimensions. We show amazing results where we get in random walks on an infinite lattice in various dimensions. And the main focus will be on 2D and 3D, and how if we start from a place, we can come back to it after some time, after some point of time, after some period of time, and that is called recurrence. We'll talk about it in 2D and 3D, and then we'll at last we'll just give a finishing touch by discussing how property of infinite series is, how a result from the field of infinite series is, impacts deeply the results of recurrence in 3D and 2D. And the idea would be easily expandable to higher dimensions also, that that would emerge from the whole lecture and the whole thing that I would say. So I know I have thrown a bunch of information at you very quickly, but I'm just going to demystify everything in this upcoming 1 hour. So I start this lecture with this quote by Shizuo Kakutani. A drunk man will find his way home, but a drunk bird may get lost forever. So initially, it might look like like Shizuo is a poet, but in fact, he was an American mathematic. He was American mathematicians, and when mathematicians talk about drunk persons, they usually refer to random walkers like things. So I hope all of you know about random walks. Rajnish, like, do you know what random walks? Rajnish?
Yes,
Okay, then that's great. So yeah, that's great then. So it will be like time saving for me. So nice. So I would start with the first topic, So the idea was to start with Markov chains. What Markov chains are, give some basic ideas that will on which we will develop more in this lecture. So first we start with Markov chains. So I want to explain what a Markov chain is using just a minute. So I want to start with Markov chains by giving an example. So Markov chains are a kind of graph. These Markov chain, the concept of Markov chain is a topic in graph theory. And what a graph is basically a set of points and edges. I mean, yeah, vertices and edges that you connect. And Markov chain is a kind of graph. It is a directed graph that shows transitions from states to states that happen with a specific given distribution of probability. And to explain that further, I'll just give you an example. So let's say I'm wearing a white t-shirt today. So you can say that I'm in a state where I'm wearing a white t-shirt. So let's say I have three t-shirts, white, blue, and let's say I have three t-shirt, white, blue, and red. Let's say so. I have three states, white. This is my current state that I'm in right now. I have red. I have blue. So maybe tomorrow I'll be wearing blue or maybe red, and then next day after that I'll be wearing blue and any other t-shirt. So so that defines my state, the state I'm in. So whether I would change to wear blue t-shirt tomorrow or a red t-shirt tomorrow signifies a transition from white to red or white to blue states. So that we can show by an arrow. And we can also say that let's say I don't take a bath tomorrow and I'm wearing the same t-shirt again. So now all these transitions have a certain chance of happening. So let's say this happens by a chance of 0.5. This happens by a chance of 0.3. And there is 0.2% chance that I don't change my t-shirt tomorrow. Now, same thing can happen with red and white. Like let's say tomorrow I'm wearing red, then what is the chance, like what is the distribution of probability that I'm wearing white on the next day? So it could be 0.4, this could be 0.4, and this could be 0.2. Same for blue, we can draw 0.5, 0.5, and this is 0. So when I wear blue dress, I just take bath every day. So now this kind of graph that you see is a Markov chain. It shows that we have three states. In general, we can have a larger number of states, and such again, these states can be connected. And this thing that you see here is a graph. Graph, as I said, is a set of vertices. So W, R, P are vertices. And the paths that you see, these are edges. And they can have multiple edges. So basically, these are directed graphs that their edges have some directions. So and each with each
Anubhav,
Hello, Anubhav.
you currently on mute. Can you please turn your mic on, Anubhav? अरे माइक ऑन कर लो.
Oh, wait, was I muted all the time? I don't think so.
So, like before you started Markov property,
Okay, okay. I think something happened. I don't know.
Yeah.
Maybe I pressed it wrong. Okay, okay. Okay. So I'll repeat from Markov property that basically it's a property that so this chain that I drew here are actual results like a coin toss that you get some results. So here in a state, the state is white shirt, this is red shirt, blue, so it goes on like that. And the fact that I'm changing the t-shirt, the process that I change the t-shirt every day, I make a transition from one state to another every day, is a Markov process. Now, the Markov property says, and it is specific to Markov chains, and it's a defining factor of Markov chains, that the result that I get on fifth day does not depend on third, second, or first day's result, but only where I stand on the fourth day. The things that govern what I wear next day are only the state where I am doing right now and the given distribution of probabilities. So this Markov property ensures that the history has no effect on the ongoing course of future. And that allows us to do one special thing. That is, we can forget about the history and it gives us the freedom that we could do anything with the history. So yeah, so it says that the Markov property in proper definition says that the evolution of a Markov process in the future depends only on the present state and does not depend on past history. And this gives us freedom to do anything about the history of the Markov process. So let's say you come to me on fourth day and you say that, Anubhav, uh, what were you wearing yesterday? So if I'm a random walker, let's say I'm a drunk person, then I don't remember what I did yesterday, and it doesn't matter to me now. So even if I had even if this was the first day, this was the second day, this was the 20th day, or it has been running indefinitely from before, it doesn't matter. The history, we can assume anything about the history. Markov property ensures that the process forgets about the history and goes into the future without any issue. Now, why I am pressing so much on this Markov property? Because it is very clear that you understand how it actually impacts the process and how it's going, and and what freedom it gives us to do with the history, that because this will allow us to clarify some future topic that I'm going to discuss after a few things. So yeah, so now the thing that I'm going to discuss is the topic of recurrence. So recurrence itself is a topic that is a property of states in a Markov chain. And with proper definition, we can extend it to Markov chains itself. That Markov chain can also be recurrent, or a state could be recurrent like that. So what do I mean when I say recurrence? So for that, I would like to draw a special kind of graph. Uh, a special kind of Markov chain. Let's say we have three states, A, B, C. B can go to here, B can go to here, you can make a change, we can come to itself. Let's say this is 0.5, 0.2, 0.3, and then A goes to C, 0.5, A goes to itself with 0.5, C goes to itself with 0.5, and C goes to A with 0.5. So let's say I start the process at B. So on the first day, I am at state B. Now, next day I could be on B again. I could just revert back to the same state, or I could go to A or C. Now, as I start the process, at the start the Markov process, I can continue to be on B for like first few days, or I can just go to A or C on first day itself. But whatever happens, if I go from B to A or C, there's no way I'm coming back to B from C or from A. If I'm at A, I can come back to A, I can go to C, and from C, I can come back to C, and I can then go back to A, but I could never reach B. So this defines the state of B, that if I start with B, I might come to B for some finite number of times, but once I go out of this, I'll be gone forever. So if this process of Markov process runs indefinitely, the number of times I'm going to come back to B would be finite. But if the process started from A, then the number of time I would be coming to A would be infinite. I can come back to A, then I can go back to C, then come again back to A, then I can go to C. It can happen for some time, but it is definitely sure that once in a while it will go back to A. So if I start from A, the number of time I would come back to A, the number of time the state A would recur is infinity. And the number of time the state C would recur is similarly infinity as well. So what we say that we have two types of state here. One is B and one is A and C. A and C both are of same type. We call the state B as transient states. Now, by transient states, we mean the states that if we start from these states, these recur finitely many times, not infinitely many times. And similarly, A and C, these are called recurrent states. So I think I did the spelling wrong. Recurrent states. So the property that A is recurring is called recurrence. That's what I mean by recurrence. And states A and C are recurring. So this is quite much the preliminaries I decided to discuss. And by equipped with this knowledge, we can go to our main issue of Polya's theorem and extend and how it shows up in 2D and 3D. And all you need to remember is what is transient state, what is recurrent state, what I mean by recurrence, and what is the Markov property and what effects it does on the history of the process. It relieves you from the history that you have had. So I have this, what I have planned. Okay. So yeah, so the next thing I have discussed is using like we go back to random walks and we discuss how random walk is also a kind of Markov chain. So I'm not going to talk about 1D random case because I'm not going to talk about 1D case of random walks because it is too simple. And all of you have been aware of what a random walk is. So you must have read it in like some thermodynamics course or some probability course. So I just start with the 2D case because that's right on the point we want to discuss. So you assume that this lattice that I have here extends to infinity in all directions. And let's assume that this point here is our origin. And we start here. Now, by the term we start here, it means that a drunk guy is standing on this point. And we assume that it is starting here, but it is possible that anything happened before it doesn't matter. So it is possible that the process, the random walk has been running for infinite days or whatever. We can assume anything we want with the history because Markov property allows us. Now, why we can apply Markov property here? Because random walk is also a special kind of Markov chain. How? You see that these points you see that like you can so let's say this is origin, this is 1 0, this is 2 0, this is 0 1 0 2, let's say. So all these lattice points can be thought of as a vertices of graphs, and these things you can see, the lines, these are edges. Now, each edge has, in a random walk, we say that all the directions are equally probable. So each edge have a value of 0.25 as the chance that that particular edge would be taken, or like 1/4. That's the chance that this would be taken, this would be taken, like that's the random walk case. Now, it is similar to the earlier case of Markov chain that I showed you, because what happens is there is a given. There's a process that goes on. The random walk is a Markov process, and what happens next from this step is completely relying on where this thing is. So maybe at some point it goes here, it goes here, goes somewhere, and then it reaches here. Then the next step would not depend that from what path it took to come here. It depends only on the distribution of probability that is equal in all directions. So any direction it could be this, or this, and that does not depend on the history. So this kind of process, this kind of random walk is also a Markov process, and hence it inherits the Markov property. So yeah. So this kind of just let me click. Yeah. So now I want to discuss that why the origin in this lattice is recurrent. So we have this Polya's recurrence theorem that is in 2D. I will discuss its general version in the last. Polya's recurrence theorem claims that in a 2D lattice, no matter where we start, we can assume any point where we start as the origin, and no matter where we start, this origin is a recurrent state. It means that if I start this process, I go to some place and I go to some place else, then I go to some other place. But if I run this process long enough, I am bound to see that at some point of time, the state comes back to 0. And it is guaranteed. The probability that this thing returns back to 0 is 1. It is completely guaranteed by Polya's recurrence theorem. And that's what this theorem claims. And in this lecture, I'm going to prove this theorem using the Markov chain properties and all that. But before I prove it, I want to show that if this is true, what else does this mean? So if I say that if I start at origin and I'm bound to return to origin after some time, what else does it mean? It means that that if we add the property of Markov chains, Markov property, if we add that here, it means that we don't know if this is the first time we are at origin. The guy who is walking is a drunk guy and they don't remember much. So Markov property allows that history can be forgotten and is indeed forgotten. So when I say that I'm starting here, I'm just saying that it's the state that I am right now. Maybe this process has been running indefinitely and right now I'm here. Or maybe I started somewhere else and I'm here at some point of time, but I don't know where I started. So if I start from the origin and I come back after some time, or I am at origin right now, I'm bound to come back to the origin. But once I come back to origin, I forget I was at the origin before. So from that moment, I can assume that this is my first topic. And then again, by Polya's recurrence theorem, it guarantees that I would come back to the origin again. And if again I come here, I forget that thing again that I was here at origin. And then again I come back after some weird path that I take. It means that every time I come here, I forget that that I was here at origin, and I'm going to come back again. And that's going to happen again and again and again until the number of times I reach the origin is infinite. So if I let this run, if this process run infinite number of time, the random walk would take its weird course across the lattice, but it will come back to origin infinite number of times. And that makes the origin a recurrent state. That's how I defined it for the Markov chains. And since random walk is a Markov chain, the origin is a recurrent state. That's what the Polya recurrence theorem claims. And if we add the Markov property, we can forget about the history. And it also gives us the freedom that we could do anything about the history. So we can assume that it started at some point here, even though I don't know if it did or not, because Even if it did, it would know, and if it did not, it would not know again. And then if we assume that in history we were at this point, at some point of time, Polya's recurrence theorem says that we would come back to this point infinite number of times. It might take a it might take a minute or two to adjust or to digest this fact that indeed that's true. And it means that if I take just two random points, I can assume any one of them to be the origin. And then it is sure that I would reach the other point infinitely many numbers of time, even this point infinitely many numbers of time. And it means that all the points in the lattice, of course, they are like non-distinguishable because it's an infinite lattice. And even if they were, the Polya's recurrence theorem in 2D suggests that any infinite lattice, if you're moving across it, you are bound to cover each and every point in a long enough run. So if the process runs for an infinite number of times, Polya's recurrence theorem has a corollary that the random walker goes to each and every place. And this is what I'm going to prove to you. And now I would like to take a minute to come back to that earlier quote of mine, like not mine quote, of course, by Sizuo, that a drunk man will find his way home, but a drunk bird may get lost forever. A drunk man, of course, is a random walker who is walking on a flat surface on a 2D space, and it is bound to cover each and every point in the space. But a drunk bird is actually moving in 3D space. And in 3D, it's not the same case that in 3D, the Polya's recurrence theorem says that it is possible that you might never ever return back to your origin. You might return to your origin for a finite number of time, as we did for B here, or B here. But as soon as you go out of like go farther from the origin, it is possible that you might never return back. So in the case of 2D, the possibility that you would return back to origin was 1, it is guaranteed. But in case of 3D, it is not. Now, why there is a stark difference? How can we prove it? Is there an intuition description of it? Yes, there is some, and I'm going to give you in this lecture. So let's what else I have that I did. Okay, so yeah, so now I start with the proof. Now I start with the proof of Polya's recurrence theorem. So how can I prove that I'm going to come back to that my origin point in 2D? So it's pretty simple. We just have to consider that we have a random walk. That we have a random walk that has been indefinitely running. Indefinitely running random walk in 2D. Or yeah, let's consider the case of 2D first. So it has been running for a long time. And what we want to intend, like let's say at some point we got at origin, and then we say that this is my starting point. I can forget about the history and I can just go on with the future. So we need to consider a quantity called V, let's say V, which is number of times the random walker returns to origin. Now, more importantly, we want to discuss, we want to consider the value of its expected value. Like, what is the expected value of V? Those who have done quantum mechanics at some stage would have more idea of what I mean by expected. But those who don't, you can just think of it like the average value of V. That's good. That's good enough. And at least in class 12th, you have done that. What it means that in probability theory, it means that this expected value of V is equal to 0 time P, that V is equal to 0. P, it means that the chances that V is 0 plus 1 dot P that V is 1 plus 2 dot P that V is 2 and so on. So you get what so you get what I'm trying to say, right? So instead of writing like this, I can write it like 0 point. So this is basically 0. So I just ignore this thing. I can. So this is by definition true. That's I have not used any fact or information from the case we are considering. But now I'm going to modify the way I write it. I will write it like this. Come here. P b equals to 1 plus p b equals to 2 plus p b equals to 3. Now I have 2 here, so I would just add one more p below it. And here I would have 3 dot p v equals to 3. So I would add 2 3s here. Same for p4. I will have 4. So now you see that if I sum just this line, this gives me, so we have v here, this gives me p that v is at least 1. In terms, it is to say that the chances that the number of returns is at least 1. It means that indeed the point returns back to the origin. The drunk walker returns back to origin. What is the chances of that? So this is this. Now if I sum just this part, this gives me p that v is at least 2. It can be 2, 3, 4 like that, and same so on. Now let's say that like I can write this p v greater than 1 as p return, that p is going to return, and let's say this is r. This is r for, like, of course r is less than equal to 1 because it is a possibility, so it has to be less than 1. So now we want to know if p v at least equals to 1 is r, then what would be p v2 in terms of r? So for that, let's consider the case here, and we're going to use the Markov property again, that the possibility that this comes back after some random motion is r, but once it comes back, it forgets that it has come back here. So for me to ask that what is the possibility that it comes back twice, would be that it comes back once, it forgets, and then it comes back again. So we have r cross r, like r cross r as the possibility that it comes back twice. And what is the possibility that it comes back n times is just r to the power n. I hope this point is clear why I'm doing it. That is clear, right? Did I explain it properly, or I think I did some, like I just said shortly? Is that clear? Just a confirmation that this is clear why I use Rn. Hello?
Yeah, it is clear because they are independent events.
Yeah, exactly. So yes, it's good. So I go back here. So thus it means that p that v is more than r is at least 2 would be r square, and then p that v is at least 3 would be r cubed, and so on. So this sum, that expected value of v, becomes a geometric progression in R. The sum is quite easy. It's just R, 1 minus R. Now we need to take a moment to understand what V and what R means and what values they can take, and under what values the random walk would be transient and what values the random walk, the origin, would be a recurrent state. So as we discussed, for the origin to be a recurrent state, the number of times the number of times the random walker returns to origin should be infinity for it to be recurrent. But if it is finite, that the origin is repeated only finite number of times, it means that the origin is a transient state. So we intend to write, voice not going up. Yeah. So we intend to write in terms of V and R that a state is transient if V is infinity or R is 1. So R is 1. And what is R? R is P of return. So if it is sure that R that it's going to return back, it means that V has to be infinity. And then so wait, just I did a mistake. I'm sorry for that. Let me correct myself. So the state is recurrent if v is infinity, that it comes back again and again and again forever, then it is called recurrent. And the state is transient if v is less than infinity, it means v is finite. And in that case, r has to be less than 1. It means that r is not 1. It means the chances that you would return back to origin is not guaranteed. There is a non-zero possibility that is equal to 1 minus r, which signifies that there is a non-zero possibility that you can just get lost in the random walk and would never come back home. Now, what we intend to show that this is indeed the case for 2D, and this is indeed the case for 3D. So how to do that? So it is simple. We just do simple combinatorics. The process of random walk can be thought of as a series of states or steps that you take. So in a random walk in 2 dimension, you can have these states up. I mean, you can take these steps up, down, left, and right. While in a 3D, so in a 2D random walk, you can take these 4 steps. In 3D, you can take up, down. Let's say, okay, let's not use arrows. I'm writing in a 2D paper. So let's say you can go up, down, and north, south, east, and west. Now, for you to come back to your origin, you need to have equal numbers of these. So like these and these has to be equal, these and these has to be equal, right? Uh, yeah, and same for this case. So like up and down. This is T for down. Down has to be equal. North and south has to be equal. East and west has to be equal. Only then you would come back to origin. Now, but before I go on more into this, just let me give you a brief idea. I had to do that one thing before this step. I just skipped that it, so or you can just keep this isolated for some moment. Just think of yeah. So expected value of v or just v can be thought of as a sum of answers of a tally of questions. So what those questions could be, that the questions we have is have we returned to origin at step 1? Answer could be yes or no. Answer could be any one of them. If it is yes, we write +1. If it is no, we write 0. This is the answer it could be. Same we ask for all the steps to infinity. Steps 2, 3, 4, 5, and all till infinity. And let's say we were back at origin on step 2 and at step 6, but we were not at 0 at step 4, 5, 3, and 1. So we're at 0. So the value of v would be just sum of all these points, like how many times it has come back to origin. And moreover, the expected value of v would be expected value of all these answers. This plus this plus this plus this plus expected value of this plus expected value of this. And what is the expected value of this? That is just P1 yes plus P1 no. So 1 means that the possibility of answering yes at step 1, and P1 no means possibility of answering no at step 1. Answering yes means that you are back at 0, and answering no means you are not back at 0. And for step 1, it is pretty clear that step 1, if you have origin at step 1, you either go here or here or here or here. By no way you can come back to origin. So P1 yes is 0 and P no 1 is P1 no is 1. So the expected value is 1 times P1, 0 times P1, which is equal to P1 yes. And for any ith step, that expected value of answer is Pi yes. The no part goes away because a 0 comes before no, because we are writing 0 when there is no. I hope that is clear. I just do not mess this thing up. Yeah, so yeah, that's quite simple. I hope that all of you got it. So all I mean to say is that the answer for each step, the expected value of answer for each step, for ith step, is PIS. And where PIS means the possibility of saying yes on the ith question. And we can simply write this as PI. Well, let's ignore the yes. So the expected value of V becomes the sum of PIs. That we ask that we have that what is the expected answer of this question, then this question, then this question, and we sum it all, we get this, where I goes from 1 to infinity, because this process indeed runs infinitely. Now we want to ask the questions that we have already noted. For the thing to come back to origin, they must have same number of up and down, right, left and right, up and down, north, south, east, west. These two have to be same, these two have to be same, these two have to be same. So the total number of steps it took for it to come back has to be even, because these are same. So these sum is even, this sum is even, the whole sum is has to be even. So it means that the answer to questions like have we returned to 0 at step 1 or any odd number of step would be 0. And that translates that P1, P3, P5, and for that matter, any 2k plus 1 has to be 0, because you can't reach back to your origin at any odd step. So now we have reduced the expectation value of V to P2n, where n goes from 1 to infinity. Because this has to be even, that's why 2n, the odd terms are gone. Now we ask a very simple question that comes that and whose answers come from combinatorics. That what is the value of P2n? So just let me repeat once more what P2n means. Is that the P2n is the possibility of reaching back to origin in 2n steps. You take 2n steps and you find yourself back to origin. What is the chance of that happening? So the chances of that happening, the answer comes simply from probability theory and combinatorics. You say that this is equal to number of ways or paths in which you can come back, in which you return to 0 in n steps, sorry, 2n steps, and divided by total total number of possible random walks. That's simple, very simple. Like that simple theory we have learned in 11, 12. Now we want to calculate this, how many ways in which you can return to 0 in 2n steps. So what options we have? If for a 2D we have up, we have a down, we have a left, we have a right. So we in total we take 2n of these. So let's say we took I of these, then we have to take I of these to come back to origin, because we are trying to find the number of way in which we indeed come back to origin. And this would be n minus I, n minus I, n minus I, because the whole sum has to be 2n. If you add, this is n, 2n. Now we want to ask that in how many ways we can how many permutations we can have of this. That would give us the number of paths with I ups and I downs, n plus I rights and n plus I lefts. So that would be simply 2n factorial by I factorial n minus I factorial n minus I factorial. That's easy enough, right? Because we all know that there are I of same repeated things. So not to overcount them, we divide by I factorial, same for I factorial these, then for I factorial of these and I factorial of these. And to find the total number of ways in which we can return to origin would be to sum this over with I, where I can be 0 to I can be n. I can be n. Yeah, I can be n. Yeah, so it goes from 0 to n. Now this is the total. Now this is equal to this, and this is the 2D case. And what is the total number of possible random walks? That is simply we have 4 options, and we have 2n steps, so that is 4 to the power 2n. So what we get is P2 2n for 2D is 1 by 4 2n times sum over n I equals to 0 I square n minus I square. This. And if you try to find the same thing for 3 dimensions, what you would get is, sorry, P2n. Why I'm writing capital N? 2n for 3D would be 1 by 6 2n. Why 6 2n here? Because here we have 4 options. In 3D we have 6 options. Up and down is also there. So we have 6n, total number of random walks in 2n steps. And this translates very simply, you can even understand. It goes to 2n factorial, the up stays same. We have I factorial square, j factorial square, and n minus I minus j factorial square. And the sum is over both I and j. Why? Because here we have 3 options: up, down, left, right, and what? And north and south. We can have I of these, I of these. We can have j of these, j of these. We can have n minus I minus j of these, and n minus I minus j of these. These have to be equal. These have to be equal. These have to be equal. The sum has to be 2, and it is 2. And if you do simple combinatorics, you get this value. Now, am I going to solve this? Am I going to solve this expression and simplify it? No. I would just state as a fact that these expressions, I mean this expression and this expression, if you calculate using Stirling formula and all that, you actually do the sum, which can be done, but I won't do it right now because it would take a longer period of time. So I would just say that these are approximately of these scale as 1 by n. For larger n, these scale as 1 by n, and similarly this expression scales as 1 by n 3 power 2. So we get that p for 2D, p2n for 2D scales as 1 by n, and p for 3D scales as 1 by n to the power 3 by 2. And we know here that this expression has to be in mind, that we want to calculate the expected value of v. Now we have p2n, we just need to sum it over n. Now, of course, there would be some constants here, and I just ignored that because I don't want the exact value of v. I just want whether it is infinity or finite. So now from those who have done series and sequences, that usually happens in first year, or maybe you don't. So even if you have not done this result in maybe you have not done infinite series in your first year, and if you have not done, you can just simply know that if you have a series of 1 by n to the power let's say just 1. So you have a series like this, n goes from 1 to infinity. This series is a diverging series. Its complete value is infinity. But if you have a series where you have power L, sum on 1 to infinity, and L is more than 1, and L is more than 1, it could be L could be like simply like 1.10001, just a tiny bit up than 1. This series will converge. So if I have a series of 1 to the power 1 plus 1 to the 2 to the power 1 plus 3 plus 4, this series diverges, but a series of this form 1.01 to 1.01 plus like that, this series converges. So so for 3D, from these two expressions, we have that for 3D, the expected value of total number of returns is of the order of this, and this thing diverges because the power is more than 1. Sorry. What did I say? This thing converges, not diverges. I'm sorry. This thing converges because the power over n is more than one, and the value would be something finite, and hence this would be less than infinity. Similarly, for v in 2D, you will have one sum over n, and this thing diverges. So we get a result that v in 2D is infinite and v in 3D is less than infinity, it is finite. So the number of returns in 3D is finite and the number of returns in 2D is infinite, which means that origin in 2D is indeed, it is recurrent state. It comes back finitely many times, and in 3D it is only finitely number of times. Once it goes to a faraway place, it is not coming back. Now, I have a proof, a simple proof that proves exactly the same thing without going into these messy things. But the reason why I did not give you that first, because so first you like you understand that how easy it is, and you basically appreciate the easy and the beauty of that proof and how clever that proof is. And and I also wanted to discuss that these terms are not just random terms. Like the power here 1 and the power here 3/2 are not just random terms. They have connection with the dimensionality. So for a different dimension, you would get a different power. And if I just give you that, let's say you have that you are in an n dimension, I can tell you what this power would be and how to know that, how to derive that knowledge is exactly correct. I'm going to show you a different proof. But before that, I would just give you a small intuitive explanation that why this thing works. So here we have proved that yes, for 3D origin is transient state and for 2D origin is recurrent state. But to give you an intuition, so in a one dimension random walk, you have two directions to walk. So either left or right. So you have the chance. So if you take one step away from origin, the chances of you coming back in next step is 1/2. It's 1/2. And if you go one step further, the chances of going back to origin is 1/4 if you just take the two steps to the back. But in 2D, if you see, you have four options. Now the options are more than what the case in 1D. And if you take one step further away from origin, the possibility that you come back to origin is 1/4, less than what you had in random walk in one dimension. In 3D, you have six options, and the possibility of coming back if you go one step away is 1/6, even less. And it is even lesser in higher dimensions. So the question is that we expect that after some n dimensions, let's say at I dimensions, it is hard enough for the random walker to ever find its way back to the home. But for a random walker in one dimension, it is a bit easier because you have less dimension. There is less space for you to go away. But in a random walk in higher dimensions, you have more options, less chances of going back to where you came from, and you might end up getting lost. So there must be a dimension where exactly that transition from the origin being transient, that you can that you can't come back to it origin after going too far away, to the origin being recurrent, that you can actually come back to it infinitely many times. That even if you are drunk, you can find your way back home infinitely many times. There has to be a transition between that property, and that transition happens exactly in between two dimensions and three dimensions. So the Polya's recurrence theorem, this paper I used a bit. So this Polya's recurrence theorem, it says that a simple random walk in ZD, D is the dimension, Z is basically like Z2 means like you have two axes, number lines, is recurrent in dimensions D in 1 and 2. So a random walker in 1 and 2 would find its way if it is walking on a surface or on a line. But if it is in in dimensions 3 or higher, it might never come back. It might get lost, it might get so far, it might never come back. And hence the quote that a drunk man will find his way home, but a drunk bird may get lost forever. So a bird is moving in 3 dimensions, a man is in 2 dimensions. Bird can get lost, man would find his way home. So this was the main thing that I want to discuss, but I still have something in my bag right now, and I'm going to show you just a bit. Well, I have many things. So first, I want to discuss that what is the clever solution of proving that indeed, like in my proof, I skipped the calculation, right? Here, I won't need that calculation. So what happened was in just give me a minute. So yeah, so in 2 dimensions, if we start at 0, 0, we can go to 1, 0, 0, 1, or 0, -1, or -1, 0. To make this clever solution, what we need to do is that when we are thinking of 2 dimensions lattice, we overlay our coordinate system with the lattice. So this is 0, 0, this is 0, 1, this is 0, 1, this is 1, 0. But what if we tilt our lattice? So what I'm going to do, I'm going to take this so lattice is fixed, but I can change my coordinate system, right? Coordinate system is mine. I can do anything I want to do with it. So what I do, I take this coordinate system, I rotate it by 45 degrees, and then I scale it down by a factor of √2. Wait, sorry. I scale it down by a factor of √2. So you see that these 2 points are getting like these 2 points are on one another. So now, first thing to clarify that the tilted thing is our coordinate system, and the horizontal thing is our lattice, that is infinite. And you see that on the lattice, if I go from here to here, in my coordinate system, I have come from 0, 0 to -1, 1. If in the lattice I go from here to here, in my coordinate system, now I have gone to 1, 1. Where earlier I was going to 1, 0, 0, 1, -1, 1. Now I can go from in my new coordinate system, I can go from 0, 0 to 1, 1 to -1, -1 to -1, 1, or to 1, -1. So you see, now it seems that every step I take, I have 2 existing random walks. So at each step, I am so now I can now what basically I have done is I have broken down the 2-dimensional random walk in 2 1-dimensional random walks. So what happens is that this 0, just see that now you can go each step. You can go from you can go to one of these, and any step you take. Let's say you took this step, you took down. Sorry, yeah, you took a left and then you took a up. So up goes for the y-axis and down goes for left axis, for x-axis. So we can think that we are having 2 simultaneous random walks that is giving a resulting random walk in 2 dimensions. So now if we have expression for P2n that we found, that length expression in 1 dimension. So just to show how this makes things easier. So let's say we want to calculate P2n in 1 dimension. We have 2n paths, and we have 2 options, either left or right. So this can be n, this can be n. This has to be, because only then you would return back in 2n steps to the origin. So how many ways you can have this? That is simply 2n factorial, n factorial, n factorial. And we'll use the Stirling's formula, which is valid for large n's, that n factorial is 2 pi n to the power e power n. Yeah. So that's the formula. So this is valid for large n is very large. And if you use this formula here, I can do that, but it's quite simple. So just okay, I'll do that anyways. So for 2 I get 4 pi n 2n to the power 2n e to the power 2n. This is basically equal to n factorial square. So I get 2 pi n to n by e to n. And p2n was basically times 2 to the power 2n because it has two options. Like this is the total number of random walks possible. That earlier we had 6 and 4n. For 2 dimensions, for 1 dimension we have 2n. I mean just 2 to the power 2n. So we do this, we get this goes away. This we get this whole things. We have a 2n here also. This comes here. So this whole thing goes away. We have this going away. This, so we get p2n in 1 dimension is equal to 1 by root pi n, and expected value of v would be just sum of these, which is 1 by pi over 1 by root n. And since the power here is half, which is less than 1, it diverges. So this is equal to infinity. It means that the origin in 1 dimension is also recurrent as per the Polya's recurrent theorem. But now, since in this lattice we have decomposed just by rotating and dilating our coordinate system, that we see that now the random walk in our lattice can be thought of as 2 simultaneous random walks. We can get that the possibility that we return back in 2 dimension is equal to the possibility of returning back along x-axis, so 1d in x in 2n steps times 1d in y in 2n steps, which is equal to 1 by root pi n squared, that is pi n squared. Sorry, not square, sorry. So now we have p2d 2n is equal to 1 by pi n in our new system of coordinates. And if you sum this up to get expected value of v, you sum this up, it indeed diverges because the power is 1. So we have proven. Now we did not have to go through all that mess, all these finding all that thing. Just from this, after this, we can just simply do this thing to get the value of p2d2n in 2 dimensions, and then by summing it we get v. Similarly, we did for like the tilt we did for 2D case. We can do similar things for 3D case. So like for simple 3D case, what we had considered earlier. Go up. Yeah. For simple 3D case, we had options of going from 0 0 0 to 1 0 0 or 0 1 0 or 0 0 1 or then you have -1 0 0 0 -1 -1, sorry, 0 0 -1. These are the 6 options before. But if we similarly tilt the axes, then we can have this as 1 1 1 1 1 -1 -1 1 1. Then 1 -1 -1 1 -1 1, and what else do I have left? -1 -1 -1. Can I do that? No, I don't think so. I can do that. Okay. So just let me revert back. Just ignore this. I don't think the values would be 1 1 1 1 -1, but it should be something similar of that kind that we had earlier. It might be some 1 by 3 or something. I don't remember, but we can arrange the axis in such a way that we can decompose the random walk in 3 dimensions in 3 random walks in 1 dimensions. So what we could get is P2n in 3 dimensions as P2n in 1 dimensions cubed. So we get 1 by pi 3 by 2 and 3 by 2. So now we get these values that is more than 1, and if we sum this to get v, the expected value of v, that would be finite. And if you recall, the same number 3 by 2 we got if you try to resolve this expression and find out how it scales. So it scales as 1 and 3 by 2. And similarly, any d dimension, let's say we have a d dimension random walk, d can be like 10, 11 or whatever. The value of this thing would scale as 1 by n d by 2. And for what values of d will the sum of these converge? That is 1 and 2. And thus, if you are doing a random walk in 1 and 2, only then you would get this thing to diverge, and then you would have the expected value of v to be infinity. You would return to origin infinitely many times, and your state would be recurrent. But if d is higher than 3 or equal to 3, you are getting a non-recurring or a transient state. So you will get lost in that space. So that was the proof in 2 different ways. And the exact surprising thing that I wanted to convey at the end of this, the finishing touch, was to think that why is it exactly at d equals to 2 that the things like they go different ways. For 2 and 1 you can converge, for 3 you can't. Why not, let's say, 4 or 5? And the answer to that comes from infinite series. It is just because that a series of this kind where converges if L is more than 1 and diverges if L is less than 1 or equal to 1. Just because of this result from infinite series, we get such bizarre transitions, we get such bizarre differences in random walks in 2D, 3D, and higher dimensions. So isn't it amazing that you get something so irrelevant like infinite series and then random walks, both different things. But it turns out that the result from this deeply affects the result in the other field. It is just because if the result was a different thing, like if let's say if this value was here 4, that for n L more than 4 only then it converges, then you would see that the Polya's recurrence theorem would say that 1, 2, 3 and what? 4. So it can go to up till 1 till 8. Till 8 it would be a recurrent state, and after 8 it would be a transient state. But since it is 1, that is why you get like 1 and 2 are the only dimensions in which random variables can return back to their original states. So that was my talk. I was quite nervous. This was my first talk ever, and I was quite nervous that I don't know I would mess up things. I did mess up a bit, but okay, that's scrap. That goes on. That happens. I hope I did a good job. I hope you guys understood. Actually, I hope you guys satisfied. But yeah, how could I forget one thing? Wait, just a second. Oh, I took a quite long time listening. I just have one interesting thing to show you. Just like some gimmicks, some simulations. I'll just share my screen once again. Yeah. So here in Mathematica, I have this code which you, if you want, you can try to run with yourself. So this thing starts at some point and then it goes to other point. And I just want to show that if the origin point, like the main starting point, has 2 lines going across it, it means that it like at least 2 lines going across it, it means that it has been returned once. So I just turn it for 100 points. You see that it started here and it returns back here. It again returns back here. Now let's do for more points, 1,000 points. It again, like you see that there are 2 points going, one going into, one going out. So it again returned back, but like just once. Of course, if I let this run for like 10,000 or 10 lakh steps, it might return many times. So let's increase more, 10,000 steps. Yeah, so now you see it indeed returned, I think so. And then it like covered the whole area, you see. And in fact, that's what the Polya's recurrence theorem said, right? That every point in the lattice would be covered. So it seems to cover the whole area. Like some dots are there, but if you let it run for infinite amount of time, infinite steps, of course, the whole dimension, whole 2D would be covered with it. So yeah, and just add one more zero and let's see what happens. Yeah, you see it is like now like the whole thing is black. You can't see any pixel also. So it is covering the area. That's what Polya's theorem says, that it goes every point around it. And in a long run, it would cover the whole space. So that was the Polya's recurrence theorem, that that says walk in ZD is recurrent only in 1 and 2, and it's transient for D3. There are there are different ways to approach this. There's one paper by wait, yeah, this is the paper where they have proven the Polya's recurrence theorem using electric circuits, that the way the voltage would divide itself would actually turn out to prove the Polya's theorem, that you can simulate random walks in lattice kind of circuits like these, where like each vertices are like these are wires, and all the squares have four resistors on their four sides, and then like, and all of them are equal and all. So I would recommend you using them. I would just I'll be sharing the PPT here. Okay, I cut that notebook. Let me see if I have that notebook. I don't have a notebook, but anyway, I would add that in that notebook, and I would share that with you guys. That you can also read. I would highly suggest you that you read that part where they prove that theorem with uh, uh, with electric circuits. So to be honest, I enjoyed this talk a lot by giving it. I don't know how you guys enjoyed by hearing it. Hi Preetham, I didn't see you. I see you at last. So I guess you can turn off the recording before giving feedback. Let's not get that on record. Sabyasachi? Hello? Holy hell. Oh, okay. I thought that I was again muted. Hello? सबको सुना दिया क्या मैंने? Hello guys. No doubts, no questions. All too simple. Hi. Can't hear anyone. Yeah. I heard some ruffling sounds from Sabyasachi. Hello? Hello?
Yeah, hello. Can you?
Yeah. You can turn the recording off. The talk is over.
Like, I'm not. I don't know how to.
Okay, Sabyasachi, let me try if I can. Sabyasachi is trying to speak something. It's not able to. सब्यसाची भाई सो गए क्या? हेलो 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 सब्यसाची.
Like he's saying that his mic is not working in
Okay,
chat.
okay. Okay, okay.
Anyways,
So,
like there's an
so
amazing.
like,
Uh,
yeah. Thanks a lot.
yeah.
I hope you got something out of it because like I thought personally it was quite simple topic, but I chose it because it was special. Like I think it felt quite good to me when I was reading it. I thought to share it. Like, you have seen that Rahul Gandhi meme, right? Like he says